everybody. You wanted a sheep dissection. Here we go. This is a sheep brain. This is the human brain. Let's look at it from the side. Sheep and human. Is it going well, Sol?
Yeah, your glove is covering most of the sheep.
Okay. Yes? All right, and then let's look at the bottom. There's the sheep and there's the human. I mean, it's very, very much smaller, obviously. But it still has that same general plan where the telencephalon has completely overtaken everything else. It's not quite as far back, so if we look down on the human brain, you don't see cerebellum. But if you look down on the sheep brain, you do. I think a huge part of that is that the sheep spinal cord is oriented back because the sheep is a quadruped, whereas in the human, let's orient it the same way, the spinal cord is going down because we're bipedal. Okay, so in the sheep brain, let's get this to a place where we can start to understand what we're looking at. Well, we already know a few things. This is spinal cord. Here's hindbrain. This is the cerebellum, and we're going to look at a little bit more about the cerebellum in a bit. Here's the telencephalon. You remember that in the human brain, we have these indentations. These indentations are formed by the roof of the orbit. The roof of the orbit of the eye. In the sheep, the eyes are off to the side, and so here's the sheep eye. It's on the side. So you see these two indentations here and here. That's where the sheep eye is. These are the olfactory nerves or olfactory tracts that are going off to the olfactory bulbs that have been cut off. This is the optic chiasm right here that's going to send its optic nerve off to the eye. And this, what they did, the supply house, when they sent us this, they sent it to us with a piece of dura for one reason, so that we could see this structure, which is the pineal. I'm sorry, it's the pituitary. This is the pituitary. So the pituitary is still connected. It's right here, and for that reason, we had to keep the dura on. But now what I'm going to do is I'm going to cut the dura off. And when I cut the dura off, I have to cut the cranial nerves. This nerve right here, this is called abducens. It's the 6th cranial nerve. And this big nerve right here that's coming off the side of the pons is the 5th cranial nerve. It's called the trigeminal. And here are our old friends, the ocular motor nerves. They're the 3rd cranial nerve. So those are the 3rd cranial nerves. And now all I have to do is cut the stalk of the pituitary. So now I'm going to cut the stalk of the pituitary right there. Ooh, look at that. There's the stalk of the pituitary. That's very cool. Boom. And now I'm off. I'm dragging some vessels with me, but now I'm separated. And now what you're going to see is that when you look at this brain, okay, there might be a little bit of initial panic, a little bit of initial, it's different from the human, but a lot of it's just exactly the same. Here's spinal cord, here's medulla, this is pons, this is midbrain, here's the ocular motor, and here is the base of the diencephalon, so the hypothalamus. And the rest of this is all telencephalon. Okay, so let's just look at the cerebellum, because when I first looked at the cerebellum of the sheep, I learned something that was never evident to me in looking at human cerebellums. So here's the cerebellum. This middle piece here is the vermis. That's that central portion. And these are the lobes. These are the lateral hemispheres, or the hemispheres of the cerebellum. One hemisphere, two hemispheres. And here's the vermis. Let's just make sure that we understand where that is on the human. Well, really, all you see when you look at the cerebellum are the two hemispheres, because they have expanded to cover up the vermis, which is right inside of there, underneath there. There's the vermis. This is vermis in here. Can you see that? Okay, good. So almost the bulk of the human cerebellum is hemisphere. The vast majority of the cerebellum of the sheep is vermis, and that is because the vermis is going to deal with things on the midline, so the trunk, the axis, the posture and gait and eye movements and speech. Well, sheep is not speaking, but we're speaking. But these are dealing with the limbs, and most importantly with the hands and the feet. But the sheep don't have digits, so they have a very small hemisphere. The really cool thing that I learned by looking at sheep cerebellum is, look at this. Is it symmetrical? Is the vermis symmetrical? Well, not so much. You can see that it takes a jog. Look at that. It takes a jog. So I saw that. I saw that on one sheep brain, and then I saw it on a second sheep brain, and then I saw it on the third sheep brain, and then I went back and I found in the neuroanatomy books that, in fact, everyone's known that, or people may have forgotten it, but people knew it for a long time. The explanation, there is no explanation for it. There's no sort of just so story as to why that would be, but it's very interesting that the vermis takes a jog, and the vermis of the human takes a jog too. Okay, so now let's see, is the inside there, is the brain similar in the sheep as it is in the human? It is. So we're going to look at how the telencephalon comes back on top of the diencephalon and the rest of the brain. So the first thing that we have to do is we have to sort of split these hemispheres, and just like in the human, there's a right telencephalic hemisphere and a left telencephalic hemisphere, and so we can look down, and when we look down, what are we looking at? We're looking at the corpus callosum, that connection between the two sides. So I'm going to cut that. Look at how it's cutting. Look at how it's cutting. Ooh, you can see that it's cutting. Okay, so then look at this. I can peel this back, and what do I see? I see midbrain and diencephalon. Look at that. And all I can do, I can basically rip this off, and what I've ripped off is the telencephalon. I'm going to make a couple of cuts here. Okay. So this is, remember we saw the telencephalic cap a few times ago? I'll figure out what that video is called, but this is the sheep's telencephalic cap. So it's not as big as a telencephalic cap in a human, but it's none too shabby when you consider that this is the whole, that this is the whole brain. right? So that's the whole brain. That's the telencephalic cap. And what do we have? We have this, which is the diencephalon. This is all diencephalon. We have this, which is midbrain, and this is actually the second really surprising thing that I learned about a sheep. Look at this structure. This structure is the superior colliculus. Don't stop recording there, Sol. We're going to just look at a superior colliculus in a mid-sagittally cut human brain. Here's a superior colliculus in the sheep. Here is the superior colliculus in a human. I would actually say that the sheep superior colliculus looks bigger. I think that's very bizarre. I do not understand that, but that's a fact. Okay, so there's the superior colliculus. Superior colliculus is very important for orienting movements. I don't think of sheep as very orienting type of animals, but there you go. So this is the superior colliculus. It's part of the midbrain. And remember this, our friend, our non-neural friend? This is the pineal gland. And you can see that if this pineal gland started to grow, it would start to press down. And right underneath here is part of the ventricular system that could get clogged. And so this is a dangerous thing because it could grow and increase intracranial pressure. That would be a problem. It can also grow and press down and block the flow of cerebrospinal fluid and thereby create hydrocephalus. So that's pineal gland. This is the superior colliculus back here. This thing here is the inferior colliculus. If we turn it over, we see spinal cord, medulla. Here's the pons. And just like the hemispheres of the cerebellum are small, the pons is small. Let's compare the pons of the human. I guess I should orient it the same way. So in this thing right here is the pons. That whole bulbous mass here is the pons, and you see that it's feeding right into the cerebellum. Here's pons, it's going right into the cerebellum. Here is pons, and it's also going right into the cerebellum. Do you see that? Okay. So in front of pons is midbrain. Here's the midbrain. These are the oculomotor nerves that control voluntary movement of the eyelid, plus a lot of eye movements, including all the vertical eye movements. And then in front of that is diencephalon. What we're looking at here is hypothalamus, and then back up here is thalamus. So let's compare once again the pons and the cerebellum. Here, I'm just reminding you, here is the pons, the base of the pons. This is the part of the pons that is married to the cerebellum, in particular to the cerebellar hemispheres. So this is big in us because we have these big, or they both got big together, the cerebellar hemisphere and the base of the pons. And here's the sheep. Here's the base of the pons. Here's the cerebellum. They're both connected. I'm going to just cut off the peduncle. I'm going to cut the connection. Okay, there you go. I am cutting off the cerebellum. There is no other structure in the brain that has so constricted an access. So the cerebellum, if it were not for these peduncles, it would not be part of the brain. It would float off. So that's the only way in or out. Were you going to say something?
Yeah, so are they connected to the hemispheres and not the vermis, or how is the...
It's connected to, so this connection is to the entirety. It goes both to the vermis and to the hemispheres. So now we look down on it and we see this structure, which I haven't really talked about, but this is the fourth ventricle, and it's going to contain cerebrospinal fluid. And it goes right into this aqueduct, which I'm putting my probe into. And so it's going right into the third ventricle, which is part of the midbrain. And you can see I'm in midbrain. Here's the colliculi, the superior and inferior colliculi, the bizarrely large superior colliculus. Okay. So yes. Small hemisphere, small basis pontus. Let's cut this mid-sagittally. I'm so sad because the pineal just came off. That was very unfortunate. It slipped off, but at the very least, what did I do? I cut it right on midline. Yay! Look at that. How do I know? Because there is the aqueduct. You see how that leads? That's a little channel that's leading from the fourth ventricle up here to this third ventricle, which I cut a little bit off center, but not much. This is the third ventricle. Let's get that little bit off. Okay, great. So fourth ventricle, aqueduct, third ventricle. And regrettably, I cut off the pineal. There it is. But the pineal would sit something like that. And so if the pineal grows, it presses right here. And that's why it presses right here. It can close this aqueduct, and you can imagine that that is a very vulnerable place where hydrocephalus could occur. If we look at it from the side, let's see, which side is this? Okay, we're going to look at it like this. So let's compare the sheep and the human. We don't have a medulla, but the medulla on here, we don't have a human medulla, but here it is. Here's the medulla. Here's the spinal cord. Here's the pons. Here's the pons. Here's the midbrain. Here's the midbrain. Here's the diencephalon, and here's the diencephalon right here. And then here's the telencephalon. So the same parts, they're proportionately bigger or smaller, but we've got the same parts. Okay, now the final thing that I want to do is explain to you about the ventricles. That's what we'll do next. Okay, so now what we're going to do is we're going to look at the ventricular system. And we really didn't emphasize this in the course, but inside of the brain there are these spaces that contain cerebrospinal fluid, or CSF, and they are within the telencephalon. There's a piece of ventricle in every section. So within the telencephalon, it's called these lateral ventricles. That's this C shape. And then in the diencephalon, it's the third ventricle. In the midbrain, it's the cerebral aqueduct. In the hindbrain, it's the fourth ventricle. And from the fourth ventricle, CSF leaks out. This is really cool. It's really cool. Okay, so here's the the brain, and there's a leaking point right here called the foramen magendie, and then there's these two leaking points over here on either side, the two foramen of Luschkas. Well, no, one foramen of Luschka, two foramina of Luschka. The fluid, the CSF, flows back from the lateral ventricles of the forebrain, of the telencephalon, back through this third ventricle, which is in the diencephalon, through the cerebral aqueduct, through the fourth ventricle. And when it gets to the fourth ventricle, it comes out through three holes. This is one of them, foramen of magendie, and then on either side, 1 and 2, there is the foramen of Luschka. So there are three holes. Foramen of Luschka on the left, foramen of Luschka on the right, and magendie. And these three holes, CSF comes out, and then it covers the convexity of the outside of the brain. So the CSF is then between the brain and the dura. It's in the subarachnoid space. That's where the CSF is. It's the fluid within the dural sac, and it surrounds both the brain and actually the spinal cord. So it surrounds the entire central nervous system, brain and spinal cord. So that's where the CSF is going to come from. It's the same deal on the human, although unfortunately this specimen doesn't have a great medulla, but it's coming out from this middle section and then also out from on either side.
What happens to the CSF after?
So what happens to the CSF? There has to be a drain. If we didn't have a drain, we would have a problem. And what happens actually is that it gets taken up by the arachnoid. The arachnoid takes it up and puts it into these things called dural sinuses. So there are things called arachnoid granulations that are going to scoop up CSF, used CSF, put it into the sinuses. The sinuses drain into the veins of the body and back to the heart through the vena cava. Okay, so in the next section, we're going to look at all the ventricles. Okay, so we're gonna go backwards through the ventricles. Back here is the fourth ventricle. This is a side view, and we saw earlier that's looking down on the fourth ventricle. The sheep, so that's looking down on it. That's the side view in the sheep. This is a side view in the human. And from there, we go to the cerebral aqueduct. The same thing. There's a cerebral aqueduct in the sheep. There it is in the human. Here is the third ventricle. It's a midline structure. Here it is in the sheep. Here it is in the human. Okay, so here's the third ventricle, and this hole right here, that hole goes over, and you can see the probe coming out on the other side, because
you can't see it.
You cannot see it? Okay, hold on.
Oh, there you go.
Yep, see that? So I went through to the side. This hole is called the foramen Monro. It's spelled without an E, so M-O-N-R-O, Monro without an E. And it goes, there's a Y. So from the third ventricle, there's a Y that goes out to the left ventricle on either side. And that's what this is. This is, I've just sort of torn back the septum, and this is the this is the lateral ventricle. This thing that's overlying it, this is the corpus callosum, if you remember that. Let's get some of this septum out of the way. Okay, so we can kind of see what's going on here. All right. And what you notice is that there's this smooth cavity here, smoothly lined cavity, and that is the lateral ventricle. And then there's this crud in it, this thing, and this is the choroid plexus. This is the tissue that makes the CSF. So the CSF is just being churned out. We're making a lot. I can't quite remember how much, but on the order of a liter or so each day. So a lot. And it has to, so the pump is in the lateral ventricle, or the biggest pump is in the lateral ventricle, and it goes backwards through the foramen Monroe to the third ventricle, back through the aqueduct, through the fourth ventricle, out Magendie and Luschka, and the two Luschkas, and then that surrounds the whole brain. And so any interruption, any blockage, if we block that third ventricle, which is really easy to close, if there's any pressure, if we block there, then the CSF backs up, and now there's too much CSF, the choroid plexus keeps pumping, there's no way to drain it, and that causes hydrocephalus. Okay. So now let's follow the lateral ventricle, and there's no good way to do this except for to sort of dissect it by tearing it. That
see it perfectly.
Yeah. So you can see it goes all the way forward to this frontal pole. Do you see that? That's the end of it. So it's going all the way forward, but the really cool part is as we go backwards. And so we're gonna follow it as it goes backwards. Look at that. I mean, it's very pretty. I think it's very pretty. And you see it's diving down, but do you see that it dives down and it goes back? And so let's follow it as it goes back. Look at that. We're going back to the occipital pole. So there it is. There it is. The frontal pole, back through the body, back to the occipital pole, back here, and then it takes a turn and it goes down in there. Where's it going to? It's going to here. It's going to the temporal lobe. Do you guys see this? This is the C. The brain is very University of Chicago, and it has a C, just like the University of Chicago logo. So it comes back here, it has a backward spur before going down to the bottom of the C.
So it's a C off the midline, a little.
It's a C that, yes, that goes around like a ram's horn. And so now let's try and follow it as it goes into the temporal lobe. And we're going to pick it up right here. Okay. Look at that. There we are. There we are. There we are. And we see our friend, the hippocampus. So all I've done is I made one little cut to reveal. I'm going to have to make a little bit more of a cut just so that you can see it. We'll take a little bit off of here. Okay. So, what do we see? We see this. We see this ventricle going all the way up to the pole. This is the front of the temporal pole. Do you guys remember? This is the back, this is the front, cerebellum, temporal lobe, and there is the lovely hippocampus. In the temporal pole of the lateral ventricle. So this lateral ventricle has gone like this. It sent a spur back here, and then it came all the way front here. So let's do one thing. Let's just take a look at this. Can you get that? Mm-hmm. So you can see This is back at the end of the occipital pole. This is where, right down under here is the hippocampus. This is the temporal pole of the lateral ventricle, and that was the frontal pole of the lateral ventricle. A nice C, okay? And if you look down on it, you can see that it's not in plane. It comes out as it goes forward. Do you see that? It comes out as it goes forward. Shall we just look at that one more time because it's so pretty? Okay, one more time. Here is we're going forward to the front of the lateral ventricle, back, 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 to the back pole, which is really close to the occipital pole of the brain. So front to back, and then around to get that temporal lobe. Can't forget the temporal lobe. And there it is. There's the part, that's the end of the lateral ventricle in the temporal lobe. And all along the way, there's this stuff, this choroid plexus. So it's being churned out of the lateral ventricles. Churned out of it also gets produced in the third ventricle. It also gets produced in the fourth ventricle. It does not get produced in the very vulnerable cerebral aqueduct. You wouldn't want to put choroid plexus here because it would possibly clog this up, and then everyone would have hydrocephalus. So we don't want that. The same deal that we just saw in the human is also true in the sheep. And so we'll just quickly look at the sheep ventricles. Okay, so I cut far enough down, and there I've entered the lateral ventricle. I can